Okay. We're starting. So we're going to continue with 6.2 and finish up those examples. Okay, quick, what's this? A to U times U prime. How do you know you have to put a U prime? Yeah?
It's derived with respect to x, not u.
Derivative is with respect to x, not u. So u is something other than x, so you have to multiply by its derivative. That's the chain rule. Right? You think of u as some function of x. Okay? And what's the derivative e to u prime e to the u. What is log to the base a of a to the x? What's ln of e to the ln of x? Okay, okay. Alright, big shots, let's see. Where are we? We did the limit, we did the derivative of e to the x squared and e to the x, I feel like we did that, and e to the, do we do the derivative of 2 to the x?
Yeah.
We
And
did all
5
of
to the x cubed?
Yeah, we were to the integrals.
Did we do any of the integrals?
No.
We did none of the integrals. Okay, so these are the rest of the examples. That was the integral of x e to the x squared, x. The integral of e to the radical x of the radical x. The integral of 3 to the x dx. X squared 5 to the x cubed plus 1. Okay, I don't think I gave you this, but let's just actually do this one. Relabel this, I know it wasn't like A, B, C, D. Let's relabel this. Okay, A, what do we do? How's it done?
So you can notice right away that obviously it's not going to be a simple thing. It can't just do that. So you're going to have to see if there's some sort of a u sub, and it's kind of indicated that might be a process for the fact that x is a part of the derivative of x squared.
Okay.
So you could do a substitution u for x squared, and then go from there.
Okay, so let u equals x squared, how do you continue?
And then derive both of those, get 2x dx.
dx,
And given in terms, get the dx alone, so divide du by 2x.
Okay.
To kind of show that, and then when you
So
throw
now
that
you
u
start
in,
to plug them in, right?
yeah, the x and the x will cancel, you'll get 1/2.
And that becomes e to the u, and then the dx becomes du over 2x. The x's cancelled. That becomes 1/2 integral of e to the u du. And what's the integral of this? Just itself. And so now we weren't asked the question in terms of u, we're asked it in terms of x, so we have to back substitute. And so that is the answer. And of course, with integration, you can remind yourself of this. You can always check that if you differentiate this guy, you should get, well, I didn't write here, the original integrand. You should get that guy back. Okay? And you can, if you apply the rule that I asked you about earlier, u prime e to the u, you realize that u prime would be 2x, it comes down, the halves cancel, you're left with the x, and then you have e to the x squared, derivative of plus c is just going to be 0. Okay, so you can always check your answer with integration by differentiating your answer to make sure you did the right thing. What you do not want to do, remember that you don't want to do, is that the integral of a product is not the product of the integral. So if you start by like integrating x separately and then try to integrate that and to actually stick them together, that would be wrong. In fact, what is the integral of this? Let's say it was e to the x squared by itself. What would you do? And the answer is it can't be done. So that's a trick question. So the thing with integration is a lot more difficult than differentiation, and we'll see that we're going to do a lot of integration techniques in this class, and you'll see how much more challenging that is than actually doing derivatives back in Calc 1. But one surprising thing about integration is sometimes you can have a relatively simple looking function and you can't actually integrate it. There is no antiderivative, meaning there is no function that you can think of that when you perform derivative rules on it, you would get e to the x squared as a result, right? And this can be proven, like no such formula actually exists. So it's possible for integrals not even to exist in principle. There are ways, of course, if someone told us that, oh, 0 to 1, then we can actually find an answer. We can actually find an answer within any degree of accuracy that we care about, but actually to find a general antiderivative wouldn't exist for this. So even if you were mistakenly trying to integrate individually, it wouldn't even work. And sometimes it's just amazing how these things work, because if you put a radical in the power and you think that might be crazy, that one actually does have a formula, right? So you have to be careful with integrals. And we'll learn to do that when we do integration by parts. But yeah, so this is a substitution problem because this didn't exactly look like one of our basic rules, so we do substitution to try to make it look like one of those rules. E to the radical x divided by radical x. What do you do here?
Make u square root x. And then du is 1/2 x to the negative 1/2.
Right, 1 over 2 dx. And we can follow this little trick here. Du. And so now we can actually start substituting. So e to the u, I replace this radical x, but this radical x I leave alone. And I'm going to multiply, the dx now becomes this, 2 radical x du. These would cancel. There are several flavors of how you can do this little part right here. You might have learned something else, but if anything confuses you, just stop me. And so this just becomes 2 e to the u du. So that's just 2 e to the u plus c. And so that's 2 e to the radical x. So I have that one. What about the integral of 3 to the x? Ideas?
One over ln of 3 times.
1 over ln of 3 times
3 to the x.
That's actually a nice formula. Did I give you guys that formula? Or no? Maybe I wanted to see if you guys would try the power of on it, but you passed. So let's actually do this in general just to make sure that we're all aware. Let's say you have a to the x dx equals, what do you do? Okay. So we're going to use a trick that we have used before to derive formulas. I believe we used it before. Is to, or maybe I didn't know that we were going to use it. You can actually rewrite these things. Use the fact that e to the ln of anything is just a thing, right? So we have that fact. So in fact, if I say this would mean that a to the x is actually the same, and since a is positive in our assumptions, it will work in the log. So I can think of that as e to the ln of a to the x. Now that seems to make things more complicated. However, we can actually simplify the power, right? What can I do with the power according to the log rules?
Right in front of it.
The x can come down in front, so that's just e to the x times ln a. Now what you need to remember about ln a is if a is a constant, ln a is a constant. Right? And we actually know how to find the integral of a constant, right? We also know of a constant times x. This I'm pretty sure I told you guys. Integral of e to the kx dx is 1 over k e to the kx plus c. Right? So it's just in this case, my k is actually ln of a. So this would mean that the integral of a to the x dx is equal to the integral of e to the x ln a dx, which is equal to, by this formula, 1 over ln a times e to the x ln a plus c. But just remember that this guy, I can actually just rewrite it in its original form, and that's just your a to the x. So that means your integral of a to the x dx is equal to that. That's another formula that you guys can use. The integral of a constant raised to the x power is, of course, the constant to the x divided by ln a. And applying that formula directly gets you here. Okay, so we have that. And with that in mind, we're better equipped to tackle D. Ideas.
Did you ever prove why e to the kx dx is 1 over k e to the k?
I believe I did. We used a substitution.
Okay.
Correct me if I'm wrong. So this, you do a u sub, set u equals kx.
Okay.
And then your du would be k dx, and then you divide, so you get that 1 over k.
Okay.
I did show that, right?
Yeah.
Okay. I'll bet.
Sometimes you're not sure. When you're a math teacher, you tell people these rules so often that sometimes you're like, did I tell you this before? I've been tutoring and teaching, and I say these rules all the time, so sometimes I see people and I just expect, I probably told them this rule. But I guess I didn't tell you guys this rule yet. But that's how you derive it. From now on, just memorize it. How do we deal with this one? This is an x cubed, I believe.
I think x cubed plus 1, your u. And du is 3x squared. And then divide by the 3.
we have x squared times 5 to the u, our dx becomes du divided by 3x squared. X squares cancel. So we get 1/3 into 5 to the u du.
So it's 1/3, like, well, 1 over the ln of 5, and then times 5 to the x cubed plus 1. Well, yeah.
So I can write that as, now I just replace the u, that's 5 to the x cubed plus 1 all over 3 ln 5 plus c. I know after a while substitution just gets boring, doesn't it? You're just like, yeah, just do it yourself. Don't worry, I got you. Got some techniques you're gonna learn. You're gonna miss substitution. Why couldn't integrals just be done by substitution all the time? How would you do something like this? Differentiate.
Product rule?
Product rule, we have this times that. Okay. So, what would that mean?
2x,
2x, differentiate the first one,
keep the second one the same.
keep the second one,
Add plus
plus,
x squared,
keep the first one,
and then, what did I do? 2x times 2x squared, I don't know.
2x times ln 2.
2x
Oh, yeah.
times, times ln 2,
And then the term.
times 2 to the x. It's weird, but we often write ln 2 at the back because you don't really want people to get confused if all that's being ln. I know technically there are no parentheses, so they shouldn't assume that anyway, but something like this would probably be like 2x to the x squared ln 2. That's probably how you'd see it in a textbook or something. Can we simplify anything here?
Factor out a 2x
We can take out a 2x
and a 2x squared.
and a 2 to the x squared.
1 plus ln
1 plus,
2. ln 2. Or x squared ln 2, excuse me.
yes, x squared ln 2. So if you ever had to set this, for example, pretend this is a function, you would need to define the slope or where critical points are, you'd factor it, you set each individual equal to 0, and you solve for it. What would the values do? Let's say I set this equal to 0, how would you solve it? What would the values be? This equals 0 means
The whole thing.
x equals 0. What would this mean? Can that be 0? So that's no solution. What would this mean? So you'd have 1 plus x squared ln 2 equals 0. So basically you'd have x squared is equal to minus 1 over ln 2. So that also has no solution. So in other words here, x equals 0 is the only critical point. Just a little reminder there, never mind. Let's move on. That in 6.2. So the homework for that is due tomorrow.
For the homework, what
Yes.
does it mean when number 61 has a star next to it? Because I think there's 2 sections of 6.2, like for problems. So I don't know, because there's one problem 61 that's like involves IVT. Is that the one you want us to do? I haven't looked at the other one.
Oh, you mean in the textbook, the starred chapters? Yeah, ignore that, just do it from.
Well, what she's referencing is in the syllabus,
Yeah.
number 61.
Oh, you mean when I put a problem in
Yeah.
starred?
I didn't know what that
It means it's probably challenging,
Oh.
or I'm not even sure if we'll actually cover it. It's one or the other. I have to look at the exact prompt to remember what I was thinking about at the time I wrote that. Okay, but let's move on to 6.3. Which I'm going to kind of do together with 6.4 because I didn't really see the point of separating them. Log functions and their derivatives. So now we know about exponentials and their derivatives. Let's figure out how to find derivatives of log functions. And we'll learn actually a couple other techniques here while we're on the way. Okay, so to derive the derivative of ln x, then ln u. Okay, so so the question to start this off is how would we compute the derivative of ln x? I'll tell you how. We'll use implicit differentiation. It's a very useful technique, especially since we know another way to express logs in terms of exponentials. So we can get this into a form that we like and use previous knowledge. So we set y equals ln x. We want y prime. How could you rewrite this so that you don't have an ln?
E to the whole size.
E to the y would be equal to x. Now that equation, I know how to differentiate all the terms in that equation. How do I differentiate the first one? Of course, when I say y prime, I do mean dy dx here. So how do I differentiate each term there with respect to x?
dy dx e to the y.
Alright, so this is just y prime e to the y by that chain rule that we talked about earlier, and that's equal to derivative of x is just 1. So this means that your y prime is just 1 divided by e to the y. Right? I can divide by e to the y, it's never 0, so I don't have to worry about that. But what is e to the y? Well, it was x. And hence we know the derivative of ln x now. The derivative of the natural log of x.
And do we have to restrict that only to positive x's?
It's automatically restricted because for ln to work,
Right.
the x's are already greater than 0.
Okay,
So
we
it's,
don't have
it's
to
assumed.
write it.
Yeah, you don't have to. There's going to be a slight variation I'm going to do on this. Where we talk about ln of the absolute value of x, in which case you, of course, restrict, say x is not 0. But yeah, for now that's good. Also, by the chain rule, of course you can always apply the chain rule. So once you know a derivative rule in terms of x, you can figure it out for any function, right? So we can say, what is the derivative of ln u? Well, that's just going to be 1 over u times u prime, or u prime over u. You don't like memorizing a lot of stuff. I'd rather you memorize the chain rule versions of formulas as opposed to the normal version. Because even if you just apply this rule to that, it still works because the derivative of x is 1. So that's how we find the derivative of ln x. However, the natural log isn't the only log around. We can have log to some arbitrary base, right? So what about the derivative of log to the base a of x? How do you think we'd figure that out?
We follow a similar manner, and then instead of raising e to the power of that, we'd raise a to the power of log base a to x.
Okay, so you're thinking of set y equals log to the base a of x.
Yeah.
This means that a to the y is equal to x, essentially?
Yeah, and then we could follow the same manner that we did.
Yeah, so this gives us y prime a to the y ln a equals 1. So this means that y prime is equal to 1 over ln a times a to the y. But a to the y we knew was x. So this is just 1 over x ln a. In other words, the derivative of the log to the base a of x is 1 over x ln a. Another way you could also derive this is by using the change of base formula and realize that you can write this as ln x divided by ln a. And then we know how to differentiate ln x, so again it just becomes 1 over x ln a. But you could go by first principles and do this as well. The derivative log to the base a of x is equal to the derivative of ln x over ln a. This is the change of base formula, which I told you guys about a couple of classes ago. So ln a is just a constant, so you literally just differentiate the ln and leave the ln a. So it's 1 over x ln a. Either way, we have that formula. So, of course, with the chain rule, we know that the derivative of log to the base a of u is just going to be u prime over u times ln a, where u can be an entire expression. Okay, so we derive all those formulas. Let's actually do some examples now. I mean, so far, it's not, the formulas that we're using, they aren't really hard to derive. It's good for you to actually think about how deriving them on your own. I want you to differentiate. A. Quantity d dx of ln x cubed. dx of ln of e to the next 5, c dx of log to the base 5 of x e to the x. do that?
Basically, the left-hand side,
Mm-hmm.
so 3x squared over x cubed.
Right, and these can cancel, you just have 3x. Right, and that was, yeah, she just followed the formula. This is using ddx of ln of u is just u prime of u. Right, which is perfectly okay, that's exactly how I would do it. But I do want you to recognize that there was another way that we could have done it, and you'll see this come into play later on. Was we can actually simplify this a little bit. So if I have ddx of ln of x cubed, I can actually use the log rule to take that 3 and move it down. And then I just have to take the derivative of ln x. So this is just 3 times 1 over x, which is again 3 over x. So you can do it a couple ways. But this is totally fine. Here, it wasn't any trouble to do it this way. But you can imagine, if finding the derivative of u happens to be particularly distressing, you can kind of use the log rules to your advantage to simplify before actually doing a derivative. That's what I want you to be aware of. B. What's the dx of ln of u to the x to the 5?
5x to the 4th,
5x to the 4th. How did you know that?
because ln is base e, so the ln e cancels.
Right, so this, right, this whole thing basically is x to the 5th. So you just use the power rule. So now, C. ddx of log to the base 5 x e to the x.
X squared e to the x over x e to the x ln of 5.
X squared e to the x.
Well, I don't really know if I did this right, but like follow the rule, like 1 over x ln of a.
So you're using the rule derivative of log to the base a of x is 1 over x ln a.
Yeah,
Okay.
and then I took the derivative of the inside, following the chain rule, but I don't know if this is right.
Okay, so it's probably better that you use the chain rule version, right? Think of this as a u,
Okay,
think of that as a u, and then on the top you put u prime.
yeah,
Okay. So what was u prime in this case?
oh, e to the x plus, x, e to the x,
Do the product rule,
yeah, got it.
and then you divide that by that thing, and then you multiply that by ln of the base, which is 5. And this is just directly applying this rule. Exactly how I would have done it, but again, I just want you to be aware of the fact that we could have done this. Right? You can actually use a log rule to split up a product. And then this one I can do the simple version of the rule. This is just 1 over x ln 5 plus this guy. Derivative of e to the x is easy, that's just itself, over e to the x ln 5. And you can actually create the common denominator and blah blah blah. You can combine these fractions and you eventually get here. But you could have written your answer in this form and that would also be fine.
Could you simplify?
Yeah.
Take out the e to the x on the left. In the first verse.
Well, I could have done that. I wouldn't think of that as simplifying though. You could have split this up, e to the x over x e to the x ln 5 plus x e to the x over x e to the x ln 5. And in this case, the e's would cancel and
I just meant like cancel the e to the x in both the numerator and the denominator. Like factor it. Take the e to the x out.
oh, you mean as, oh, okay. You could do that, yes. I wouldn't particularly care, but yes, sure. You could factor this out, 1 plus x over x e to the x ln 5, and then cancel this. 1 plus x over x ln 5. So yes, you'd realize that the e's would cancel in either case. What else is there? D. Differentiate log to the base 2 of x. Yeah?
1 over x ln 2.
Direct application of the simplest formula for the log to the base 8. Okay, move on to E. Breezing through these. Log to the base 7.
So if we blast that with a couple of log properties, you can expand it out to 1/2 log 7 of x. Pull out that 1/2 power, and then plus log 7 of x plus 1.
Yeah. Which while you could do it, you could either do the product rule here, or you can write this as x to the half and multiply out, and you get like x to the 3/2 plus x to the half. You could do the power rule and get the derivative that way, but having the fractions around is probably kind of annoying. It looks a lot nicer to actually rewrite it this way using the log rules. I can separate it into a plus because there's a multiplication here. The x I can write the radical as the half power, and I can bring the power down because that's a log rule. And so now I can actually just do each of these individually. Right? So this one just becomes 1 over x ln 7 times the 1/2 that's in front, don't forget that, plus this is just going to be, the derivative of this is 1 over that thing times ln of 7. And you can combine the fractions if you want, but I'd be fine with leaving it like that. It's this one.
We could choose a chain rule for that. So you get the derivative at the top, which would be
This,
so the derivative inside, which would be -7 sine x, I believe, over that quantity times ln 3.
so That was just the u prime. Where this is the u. Basically, I wanted to see if you remember how to differentiate cosine. Oh, this example, G. What would you do here? You go, oh. Yeah?
If you were to take the natural log of it, then couldn't you split it up and make it a lot more easier to differentiate?
So yeah, so as Graham said, step one is to go, oh. No way. So now you want to try to find a better way. Okay? So, but we know about logs that they simplify multiplication, they simplify powers, they do all sorts of these other things. So here's the strategy. Set y equals this guy. And what I'm going to do is I'm going to actually take the ln of both sides. Of course, my x is greater than 0 here, so I can't take the ln of this. Ln of. Why would I do that? Well, I can simplify this guy now based on the log rules. That is going to be 1/2 ln x plus 3/2 ln of x plus 1 minus 7 ln of 2x squared plus 1. This guy here is just ln y, of course. And so now what I can do is I can actually differentiate these. It's not so bad. Applying the chain rule everywhere, I get the derivative of y divided by y equals, here derivative of that is 1/x. Here the derivative of this is 1/x plus 1. Here the derivative is going to be the derivative of that guy, which is 4x, divided by that guy. And so that means my derivative is actually equal to y times all of that mess. In other words, the derivative is equal to that thing times 1/2x plus 3/2 times x plus 1. So it was 28x over 2x squared plus 1. And of course, you can imagine if you were to do the quotient rule on that, you'd come back and you'd be like, Jhevon, your quizzes are so unfair. It took like 20 minutes just to do that one problem. But no, the trick was to use a logarithm to help you. And it turns out that this kind of method works out in general, usually, as long as you're in the domain of the logarithm. It's called logarithmic differentiation. And I'll outline the steps for that later in our next class. Show you how to use it and when you'd want to use it. Sometimes it's clear when you don't want to attack something directly. So we didn't finish 6.3 and 4, but homework for 6.2 is due tomorrow, and we'll finish this section tomorrow.
Will 6.3 and 6.4 be on the
No, the quizzes are on the previous week, so
Oh.
nothing today you're responsible for.
6.1 and the preliminaries first, 6.2 and 6.4.
Yeah.